Hello, my name is Vikrant Jain, and this is my video presentation for Lab 3 of Physics 2211. In this lab, I shall explore the application of Newton's second law, momentum, and Newton's law of universal gravitation in a situation involving a star orbiting around a black hole. The purpose of this lab was to create a computational model of the star's motion using those three components and to analyze how a change in any of these factors would impact finding the mass of the black hole. As we shall later see, there is a significant conceptual difference between Fnet and dp/dt, as well as their parallel and perpendicular components. As the orbit of a star around a black hole was examined in this lab, the system was set as the star. The position versus time data points from the star's orbit, which was given from a CSV file, and the momentum principle, as well as the equations derived from that principle to calculate the mass of the black hole. First, let us note the equations tied to the primary concepts involved in the lab. First, of course, is Newton's second law, which is shown here as final velocity equals initial velocity plus the net force over mass times delta t. Fnet itself is shown as the change in momentum over the change in time. It can also be defined as the sum of Fnet parallel and Fnet perpendicular. Similarly, dp/dt can be defined as the sum of its parallel and perpendicular components as shown. Momentum, or p, is shown to be the product of mass and change in velocity. Now, let's take a deeper look at its perpendicular component, which is equal to the quantity mass times velocity squared over r. This is a significant point to note because of the circular/elliptical motion of the star around the black hole, which thus involves an application of the concept of centripetal force. However, perhaps the most important formula to be aware of for this lab is the magnitude of Fnet being equal to the universal gravitation constant, which is 6.6 times 10 to the negative 11 times the product of two masses, which in this case would be those of the star and the black hole, divided by r squared. This formula refers to Newton's law of universal gravitation, which, as its name suggests, states that all objects attract each other with the force of gravitational attraction, that gravity is universal, and also it states that since the gravitational force is directly proportional to the mass of both interacting objects, more massive objects will attract each other with a greater gravitational force. Because this lab was so heavy on computational modeling, it is very important to touch on several key aspects of the Python code used to generate the model of the star's orbit. In terms of the system properties, the mass of the star was 1.9890 e to the 30th kilograms, and the position of the black hole was set in vector form as negative 3.00 e to the 10th, 4.00 e to the 10th, and 0 for the z component. Having this position was key to finding the relative position and distance of the star. The time step involved was 86,400 seconds. By iterating through the star's position values, the change in velocity and therefore the change in momentum of the star over that period can be determined. The corresponding derivative, the change in momentum over the change in time, follows. The Python code thus incorporated the key formulas discussed previously into its structure, with the parallel component of the change in momentum being the change in the magnitude of the momentum, and the corresponding perpendicular component being the difference between the overall change in the momentum and its parallel component. Finally, the mass of the black hole was computed using this portion of the code, which involves Newton's law of universal gravitation. When the module is run, the simulated orbit displays both the components of the change in momentum increasing as the star approaches the black hole. The parallel component points forward along the star's motion since the velocity of the star increases. As the star passes the black hole, the parallel component decreases, and at the moment the star passes it, it flips to the point opposite the direction of motion, showing how the velocity of the star decreases as it heads away from the black hole. The direction of the net force, however, always acts toward the black hole. By running my computational model, the result was a mass of 2.212 e to the 31st kilograms for my black hole. Now, one important point to note is that although Fnet was set equal to dp/dt in this Python code, there is a fundamental difference between Fnet and dp/dt, as well as their parallel and perpendicular components. Fnet represents the total sums of the pushes and pulls on a system, while dp/dt is the change in the system's momentum due to an outside force. Also, in this lab, if the black hole was replaced by a new black hole and the star's observed motion remained the same, it would appear identical, and we would conclude that the black hole had the same mass through Newton's law of universal gravitation. So, in conclusion, by observing these key applications of Newton's second law and how it works with the momentum and the law of universal gravitation, this lab was carried out successfully with the analysis of a star's orbit around a black hole. Thank you.